go. Let me start with the last bit because I also have to record the lecture.
Okay, let's go.
So, yes. So, good morning, everybody, guys. It's a pleasure to have this morning here with us Jean-Michel from Naver Labs in Europe. Jean-Michel is a research fellow at Naver Labs, and previously he was leading the research and recommendation team always at Naver Labs. His research focuses on exploiting unstructured data, so the text, speech, images, what we deliver in this course from multiple heterogeneous sources. He is leading and has led a lot of research projects covering various technical domains, including natural language processing, search and recommendation, fairness and bias in machine learning, and privacy preserving information. Yeah, is artificial intelligence or information access in your case?
Information access.
Right, thank you.
Sorry.
So thank you very much for being here, Jean-Michel. And this morning we will talk about fair ranking in information retrieval.
Okay, thanks, Nicola, for this very nice introduction. And for me also, it's a pleasure to give this lecture, especially on a topic that I appreciate very much, namely fairness and ethics in IR, so in information retrieval, and in recommender system as well. One of the reasons I like, or I'm very sensitive to this topic, is the fact that Naver, some years ago, was suspected to, so Naver is basically a search engine in Naver. It's the main search engine, is the Korean Google. And so several years ago, Naver, the search engine of Naver, was suspected to promote some kinds of, or to give more exposure to some parties, political parties than others, when they were recommending news to their audience. And so clearly this was a problem. And there is now a fairness committee, an independent fairness committee in Korea, which regularly judge and monitor the fairness of search recommendation engine in Korea. So even it's for you, it's not so important. There are several countries where there are already regulations that in some way give constraints to search and recommendation algorithms. I will talk to that later. Just a reason I like this topic. Okay, so first of all, what is fairness? Actually, it's a very hard question, and there is even no answer to this question. So fairness is normally defined as an equality of some benefits. It's a very vague definition across different individuals or socially salient groups. So, for example, when we consider the individual side viewpoint, fairness means that we treat similar individuals similarly. So, for example, two documents that are similarly relevant to user needs should be treated and so exposed in the same way, have equal chance to be exposed to the user. From the group perspective, what does it mean, fairness? Basically, it means minimize the difference in representation, treatment, or impact between groups. Still very vague definition. Fairness could also be considered as avoiding misrepresentation of protected groups. I suppose that you all know this. It was very well known 2 or 3 years ago that when you were typing on Google for example, white girls or black girls, you have completely different representation of this group namely black girls with respect to white girls. Just maybe this is now corrected, but it was very amazing to see the bias in the representation. The same, for example, typing CEO on Google on image search, you have a complete biased view of, and so a misrepresentation of what the CEO is, namely underrepresentation of women. So letting the audience feeling that or thinking that CEO is normally only men. So we know that misrepresentation can link consumers and so users experiencing skewed view of the item population. So a very skewed view of the information. So for the information access, misrepresentation is something very important. And typically this is measured by the distance between proportions in your ranking and a reference ideal distribution. So for example, if you know that, for a certain profession, for a certain job, there is equal opportunity for women that men for a position, for a role, then typically you can measure unfairness as the distance between the distribution in your ranking of male versus female and the reference, for example, 50-50 ideal distribution. So of course, now we should be less vague and be more concrete for IR and recommendation. And we will define mathematically what the benefits are and how we measure equality. And we should transform all these vague definitions, unfortunately, into some, these definitions are quite subjective, but of course for us, we should transform these subjective formulation into tractable mathematical problems. Okay. So as I told you, there is no universal definition of fairness, but actually there are more consensus of what is unfair. So people know what is not fair, but not really what is fair. So as a consequence, and we will see it later in the algorithms, it's often easier to define fairness by its opposite, namely unfairness, which is typically disparate treatment, discrimination, and so on. Okay, so what are the sources of unfairness actually in retrieval and in search recommendation? There are some exogenous factors, which is first the social biases. The world is not perfect, and you should always make the difference between the world as it should be and the world as it is, and these are completely different because as society we have biases as well. This is one thing. Reality is not ideal. Secondly, we always work with data. And so, for example, collections and so, and there are statistical bias in the way we build collection. There is the sampling biases, typically also, for example, when we work with click logs, there are also other kind of biases, which is typically the positional biases in the sense that you get data that are biased and so very influenced by the current rankers or information retrieval algorithm. There are always feedback loops in the sense that typically we collect data from current rankers or recommender systems that that influence themselves the way the user is consuming the information, and vice versa. Really, it is typically algorithms extract the feedback, the clicks to improve themselves, and this behavior typically exacerbates some biases, such as the popularity bias. There is what is called the Matthew effect, which is the richer gets richer with typically retrieval algorithms. There is also in IR biases in the annotation. For example, for learning to rank algorithms where we need a reference ground truth relevance label, very often there could be biases in the annotation as well. So more in the label that there are biases than in the data. There could be also biases in the evaluation method. For instance, you note in that evaluation, there's the difference between macro averaging versus micro averaging. So for example, when computing the performance with respect to a set of queries, of course, macro averaging, that gives equal importance to every query and not favoring what I call head queries or dorsal queries. Macro is fairer as an evaluation method with respect that and it's fairer than micro averaging. Now, this was one source, the exogenous source of factors of unfairness, but factors, so unfairness could be also led by algorithms, the algorithm itself. It's called algorithmic unfairness. This is normal because a lot of the retrieval algorithms are based on machine learning models. And we know that, for example, to compute relevance, we have machine learning models that compute relevance from the data. And we have, as all machine learning models, we have statistical effects that typically are more accurate. Models are more accurate in areas, so in the feature space, with more abundant data. This is a natural statistical effect. It means that where areas with less data, the machine learning models are much less accurate. And this could be unfair with respect to the information consumer. The fact that, for example, ranking algorithms never think about the exposures. So, for example, PRP principle that I think most of the ranking algorithms are based on do not have in mind this notion of exposure. Mainly that, so for example, if two documents have maybe very high relevance, but one is maybe, I don't know, 0.0001% more relevant than another one, the second one has no chance to be the first one. So there is no real proportionality in the exposure between the relevance and the exposure. So I will be clearer of what exposure means, but it's basically intuitively the visibility that an item has in the ranking list, knowing that typically the visibility of the top element, the top item is the list in the list is. So at rank 1 is the highest, at rank 2 is a bit higher, it's a bit lower, and so on. And it is materialized concretely, for example, by the DCG concept, so discounted cumulative gain. So the discount factor in DCG is typically a way of expressing that exposure decrease with the rank. So basically, a SERP, so a search engine result page, has a limited amount of resources. I call resource the exposures that you could give to different items, so the visibility. So the visibility is fixed. And so this is a problem. You have to share this limited resource in a fair way. It's called a fair allocation problem. Moreover, very often, people don't like stochastic ranking strategies, and they impose a deterministic ranking strategy. And we will see a bit later that with a deterministic ranking strategy, deterministic policy, you could never be fair. So as soon as you impose a deterministic ranking strategy, it will be very hard to be fair. Okay, now there is another problem. Ranking is much more complex than classification. Fairness has been studied a lot for classification problems, but not so much for ranking problems. Why? So, first of all, because a ranking task, a ranking problem, consists of multiple dependent decisions. Namely, we have to take a decision for each rank in your search. And so multiple and they are dependent. And evaluation is not on a single item, it's the evaluation, as you know, is list-wise. So it's much more complex than point-wise classification. Moreover, decisions are repeated over time in the sense that users come and come again, so that actually for a single query, there can be multiple and millions of searches exactly with the same query. And this gives an opportunity for the system to what I call amortize over time or over searches. The fact that maybe for one ranking, for the same query, for a query queue, you have a certain ranking. Maybe the next time you receive the same query, you will change a bit this ranking in order to be fairer. I will explain you how we can do that. But this is important, the fact that we have multiple opportunities over time, over searches, to compensate a deficit of surplus of visibility in order to be fairer. Okay, especially this is important because, for example, relevance this is an absolute concept, relevance, but actually it's not absolute at all. It could vary over time, it vary over the users, and so on and so on. And we know that, certainly that the clicks are biased, but still a better indication of relevance than nothing, or that some kind of arbitrary annotation by external experts that could never take the place of a real user. This concept of being able to take decision over time, so correct ranking or refine rankings over time, is the concept of fairness in expectation or aggregated fairness. You compute fairness not over a single ranking, but on multiple rankings. This is important. Another problem that makes ranking, especially in search and recommendation platforms, much more complex than classification, is that the problem is multi-stakeholders. So typically take an e-commerce platform, for example. You have both the consumer, so the buyer, you have the item provider, which is the seller, you have the platform. So for example, let's take Uber Eats, for example, which is a platform for restaurants and to book food and to order food. And we have a first stakeholder, which is the delivery agent. Okay, so we should be fair with respect to all these subpopulation, to consumers, to providers, to delivery agents, and so on and so on. So for example, what does it mean? For consumer, it means that typically we want some kind of equity of performance of the retrieval quality. So we want to user have equal access to relevant content. Okay, this is the concept of fairness for consumer. We don't want that some subpopulation or groups of users have worse retrieval quality than others for several reasons, typically biases in the data, or sometimes in the algorithm. The same for providers. We don't want an unbiased representation. So typically, for example, in a job platform, job-seeking platform, for company, for workers are typically the providers, they provide the CV, and the user are the companies. Typically, we want that the workers are not hurt by a misrepresentation, typically that CEO are always men, or that, I don't know, artists are always women. So we want unbiased representation, so equal that they appear in the SERP with equal chance of exposure for exactly the same kind of required expertise. Same for delivery agent, where we want to impose some kind of good distribution of working times and wages. As I told you, this is hard to do because a ranking list, a single ranking list, offers a limited amount of resources, what is called the exposure. So each time we have to do a ranking, especially fair ranking, we have to solve an extra fair allocation of resources problem. So this extra problem, of course, is not present in classification. So let's focus on this extra problem of fair allocation resources with a single example. Suppose that you have a search engine for cooking recipes, and that you typically you Google or you type cooking type recipe, and then you get these results. Don't know whether you see. Do you see my pointer, my mouse? Yes or not? Okay.
Yes, not very much, but enough.
Okay. So typically with a single ranking, and suppose that your search engine is very good, that these are the different recipes, and these are the author of the recipes, and these are the relevance scores, and I assume that the relevance are perfect. You see that Barak's recipe is as good as relevant as the one of David, but still Barak's receive much less exposure. Just the number of ready here is the exposure. Very high exposure, a bit less, still less, and very poor exposure and virtually no exposure. So you see that if you have the opportunity to do a single ranking, a deterministic ranking, each time you see this set of keywords, this query, systematically you will be unfair with respect to Barak simply because you cannot because he receives systematically less exposure than David for equal relevance. So you understand that the only way to solve this problem, to give Barak as the same exposure as David, is some way to permute David, John, Barak each time. Okay, so for example, next time it will be Barak, David, John. Next time it will be Barak, John, David. Okay. The same for Susan and Naila that are less relevant, but Naila will be systematically under if with a system with deterministic ranking. So you should permute Susan and Naila as well. So this is very intuitive, but this is what should happen. Okay, you see that with a single ranking, you could not achieve fairness, never. But with this concept of repeated rankings, or we have this concept of amortization over searches, and it could be fair. I like to differentiate fairness with respect to diversity, because people sometimes are confused between the two concepts. So they are indeed correlated concepts, but they differ in several ways. First, fairness is often considered expressed at the content provider side, while diversity is a user-oriented measure. Diversity should be realized intra-ranking, I mean inside a single ranking. Fairness is often achieved, as I told you, by multiple rankings. One can easily figure out cases where fairness is achieved with zero diversity and vice versa. For instance, suppose I think the first case, fairness, perfect fairness, zero diversity. We have a query, you give very similar answers, but all coming from different authors. So for example, for a scientific paper, and so all very good, different authors, but no diversity. Vice versa, if, for example, for news recommendation, you can cover one single, you could cover all the topics, for example, with the same kind of newspaper. So no diversity of newspaper source, one single newspapers, but very diverse article covering sports, economics, and so on. So you see that they are decoupled. In some way, diversity, just to make the link, diversity can be expressed as fairness from another viewpoint, which is the intent or subtopic viewpoint. Don't know whether you have spoke before about diversity, what we call exogenous and endogenous diversity, which could be the fact that with the same query you could have different intents with the same query, or the query should be covered by multiple subtopics. So in some way you could make links considering that diversity is to be fair with respect to the different intents of a query, but still to be solved in a single rank. Then you will tell me, but why care? Why should I care about fairness as IR or recommender algorithm designer? First, for ethical reasons. You should be aware that even if you are a researcher or designer, you can impact the population of users, being the consumer or the provider. So you have the risk of harming or hurting one or more of the system stakeholders. Right. So, for example, with a very bad or unfair IR system, you limit the accessibility and the quality of the information for users. So you are responsible for that. Sometimes lower exposure and will give you lower reputation or lower recognition for your providers. So you have also this responsibility of not giving bad reputation to providers. There are also business reasons, namely platform sustainability. You should avoid to hurt, of course, some subpopulation, and because this subpopulation will leave the system, and there is the vicious circle. If there are less consumer, then provider will not be so interested in participating in new platform. There will be less providers and so on and so on. Sometimes also for contractual guarantees, there are contractual guarantees, for example, for paying articles, where you should guarantee that the exposure that you give to the paying parties corresponds to some contract. More importantly, there are regulations, especially I am thinking in Europe about GDPR, and especially there is an article that in some way impose some kind of fairness, which is called the article about lawful, fair, and transparent processing. So for all these reasons, it's still useful to care and to think about how to improve your fairness in your ranking algorithm. So let's focus now more on search recommendation algorithms and especially search recommendation process, and see where the unfairness could lie. Basically in the data and in the model. So I have here the typical pipeline of an IR system. And you see that for recommender system, it's not so different. You just remove the query branch and replace it by some kind of user, and here user past historical behavior, and here the user, otherwise items and item representation. So it's basically the same process, just replacing the query by the user and the context. So first of all, there could be problems. And so unfairness in the way you present your data but we know because the way you build your collection and the fact that society is always includes societal biases. So as I explained, this will lead you to unfair correlation, especially if you build, for example, relevance models. If you are based on past history, you will think that, for example, if you model the relevance with respect to the role CEO, then the attribute gender will strongly influence and certainly mislead the representation. The way you present the query or the user could be unfair. So, for example, I will speak about that later. There could be a bias Korean descending algorithm. Now in the models, as I told you, the retrieval function could be unfair. Actually, this will be covered by the rest of the presentation. And so, for example, in the typical relevance feedback mechanism, we know that the input feedback is biased because clicks are always biased, influenced by the layout, the trust, and the position biases. A lot of that are biases. And typically, relevance feedback mechanisms amplify, exacerbate these biases. So we should be careful about relevance feedback with respect to fairness purposes. Now, let's try to give some panoramic view of all the methods to improve fairness in search recommendation. But before giving some kind of short taxonomy of all the methods, some preliminary notes. First of all, the utility from the consumer side. So basically what you are doing in information retrieval is always maximize utility. So I will define this more formally, for example, NDCG or other performance measure like this. This is always considered as an important objective. So I think nobody will tell that, oh, forget about being useful, so optimize NDCG or any list-wise performance measure. It's do this, but at the same time, do also another objective, which is a fairness objective. So typically, fairness objectives have an extra objective or sometimes as an extra constraint, depending on the formulation. And some approach, by the way, you will see that they come with a single objective that mix in an implicit way what I call a UT fair objective, which is some kind of a hybrid between something which is both so useful and fair. So the first dimension to differentiate different methods is the fairness side, being the consumer side, provider side, basically. Most of the methods are either consumer or provider side, and some, but a very small number, are both optimizing consumer and provider fairness together, while still being consumer useful. The second dimension to differentiate fairness methods is whether they focus on individual fairness, so similar people should be treated similarly, when similarity is typically measured by relevance. So items with similar relevance to user needs should be treated, so exposed equivalently, similarly. Third dimension, which is typically where you will correct or compensate or enhance fairness in the search and recommendation process. I will discuss this just after. And the fourth dimension that could differentiate is what source of unfairness you are targeting. There are basically two sources, as I explained you before, either the representation, the misrepresentation issue, or the problem of equity or inequity of benefits. So some methods target the representational problem, but they are relatively rare. why most of the methods target the equity of benefits. Okay, so a short note, which is a bit personal and subjective, which is, do we really need consumer-side fairness? This is debatable. I will tell you why. So indeed, we have some issues when we try to define consumer-side fairness, especially in information retrieval. So do you think normal that I will corrupt recommendations made to a frequent user so to make the service quality similar to a cost-type user? Is this normal? Are you ready to do this? Is it really fair? It's an open question. It's an open question. Group price, we can have the same kind of questions because, as I told you, for the provider side, we have a limited amount of resources, which is the total exposure of the service. So if we indeed put one provider at first place, then we prevent the others to have high exposure. This is not the same at the consumer side because we have no limited resource. Ideally, we could be excellent. I mean, give very high quality results for any search. So the reasons for apparent unfair difference sometimes, yes, this is something, no, this is something, sorry, what is written is not what I just told. First of all, no, second, the reason for apparent unfair difference sometimes do not come from any bias. I take the example, which is known that I think two or 3 years ago, some people studied whether there were information retrieval fairness issues with respect to the gender and with respect to the age. And they came to the conclusion that, it seemed that there are problems between young people receive lower quality results than older people. Is your ranking unfair with respect to young people? But they understand, they have a deep dive and understood that the source of the difference was not any bias in the data, but the way that young people express a query in a much more, and generally express much more complex queries, or sometimes even queries in natural language. That makes the retrieval algorithms poorer in answering this kind of query. So the question is that, should I decrease the quality for older people? No, clearly not. It's my personal it's my personal viewpoint. It's better to focus engineering efforts to improve IR for these low quality, for these groups that have low quality results, rather than downgrading results for the majority. That's why consumer fairness is still a bit debatable. As I told you, we are not, as in the provider fairness case, we are not taking anyway away from a low quality user if we provide another user with better results. Okay, so they are not dependent, not the same as for provider. Okay, now we will be more and more formal, more and more mathematical. And so let's first explain more concretely what the concept that I already introduced, which is exposure. I already use that term frequently without really telling what it's right. So the notion of benefits for providers can take multiple forms. It could be, for example, in several platforms, it could be subscription. After click, you get subscribed, or pay-per-play, or pay-per-click, or revenues coming from pay-per-play for movie recommender system. But it could be, for example, an archive and like that, reputation, recognition, something less less moneyable, less related to money. So all these different forms of benefits are abstracted under the more general concept of exposure, which is simply a way to quantify visibility in the list, in the search engine result page. By the way, I don't like to use the term list because more and more, when you see the layout of search engine result page, that's no longer any form of list, but something much more complex, which is a mix of verticals and horizontal, for example, carousels. But still, you can associate to every position in the SERP some kind of exposure. So exposure has different names, for example, attention in user experience and user interface. And in our jargon of information retrieval researchers, it's called, and machine learners, it's called also examination. Don't know whether you have a look to or you have studied some click models, Nicolas, previously.
Yes, we mentioned a few basic click models. Yes. Okay,
excellent. And certainly the PBM, which is a position-based model that I will use after. And the cascade model. So examination, if you have seen the click models, is exactly what are called the examination probability in click models, namely the probability that the user put her eyes on a particular item in the search. So it's really it can even be determined by eye tracking studies, but it's really this, the probability that you will look at, particularly focus on the particular item. So this is an important, very important concept, examination, for several reasons, even other than fairness. Okay, so now exposure, I will even define this more mathematically just after. But so as I told you, fairness methods can be also distinguished in the dimension of where they are located in the search recommendation process. And so we can distinguish pre-processing methods, in-processing, and post-processing methods. So pre-processing methods, we simply ensure that the input data are free from any undesirable and potentially harmful bias. It's just this. In processing, it's some kind of generalization of learning to rank methods. So these are really machine learning methods that directly learn end-to-end from the data to provide fair and useful ranking simultaneously. So fair and useful simultaneously. We will see an example of that. Post-processing methods assume that there is already a good, useful ranking, but we will perturb it, we change it slightly or more or less slightly, sometimes more abruptly, to make the ranking more fair in an amortized way. So not in a single ranking, but over multiple repeated rankings. So more in detail, preprocessing methods. So as I told you, we want to remove any bias from the data. One could be resampling strategies. So typically to compensate for statistical bias when collecting the data. Simply, we oversample the minority groups and maybe undersample the other. And indeed, this can reduce misrepresentation. Another thing in another preprocessing method, a bit different, is telling that, so suppose that you have data that are made of click logs, and so a lot of examples where you have so SERP, so rankings and clicks or relevance. Then typically what we do is we consider that we rank. So instead of giving this as basic input for learning to rank algorithms, we change the ranking by our preprocessing method. Typically, I will give an example of one, and we will then give this pattern, so these ideal new rankings as input of a learning to rank algorithm, so that the learning to rank algorithm will learn how to be fair and useful simultaneously. So it's just one a funny way of using your favorite L2R algorithm, but you simply change your input data and the layouts, the ideal ranking. There could be also adversarial strategy. This is rather easy to understand. So basically, the idea is to learn user or item embeddings, so representation, statistical representation, in such a way that predicting the group membership, so the protected attribute from, so for example, the gender or the age and so on, something which we should not be discriminated on. So which a discriminator, so I mean a classifier that tries to predict the gender, or for example, the age, by having as input this embedding, should be unsuccessful. It means that basically, if you succeed in having representation, so user and embeddings, such that the combinator is very bad, it means that, okay, good, your embeddings, so your user and item representation are very good, and you could use this as new representation for learning to rank algorithm, for example. Okay, this could be considered as one way of pre-training embedding of further use. You already pre-trained it in some way that removes any discrimination. In processing methods, we will see an example after, but typically it's purely machine learning methods. It's learn to rank, so machine learning, not learning to classify, but directly learning end-to-end to provide a ranking. And this is typically done by introducing a supplementary, an additional differentiable fairness oriented term in the loss function. So we have the standard utility term in the standard learning to rank loss function, and we add an unfairness term, extra term. So, but there is typically another change with respect to the standard learning to rank framework, which is extending the class of ranking strategies to be stochastic. Because as I told you, it could never be fair without stochasticity. And moreover, we will see that introducing ranking strategy, stochastic ranking strategies made the problem more differentiable. So you know that typically learning to rank methods use, for example, gradient or stochastic gradient method. And so differentiability of the loss function is very important. Having stochastic ranking, it's one way of making the problem differentiable. And finally, post-processing methods. So supposing that you have an initial very good ranking, but only useful, okay, then we will see, but we will use amortization. I mean, designing a sequence of different rankings for the same query to ensure dynamically, so on average, some kind of equity of exposure. I will focus a lot on these kind of methods just after. Okay. Now, I hope that will not be lost by the fact that we will be more mathematic now. Introduce some notation first. First of all, the relevance, I will note by row of a document that could depend on the context, X. X is something very generic. It could be a query, could be a user recommendation. Sometimes it's both query and user. In that case, by convention, when I call, so row with a hat means simply to emphasize that sometimes it's not given, but it's the estimate. So when you see the hat, row hat, it means simply that it's an estimate value, typically by counterfactual evaluation with click. So typically when both query and user constitute the context, I will use row hat simply as the expected value of the relevance of the document with respect to query average over all users. Some kind of mean relevance across all users that contribute to audience. A ranking, you know what it is. It's a ranked list of K items. And we denote the item at position K by sigma of K. And the position of an item in a ranking is the inverse permutation sigma minus 1 of D, just notation. So sigma exponent minus 1 of D is simply the rank that sigma offers to D. We denote the features associated to an item context pair by phi of D and X, as usual, in the rank framework. Now an important concept, which is the particular exposure or examination probability at a rank K in a ranking sigma. I denote this as gamma of K sigma. So gamma K sigma is the exposure that sigma gives at rank K. So this value depends on the click model, on the assumed click model. So for example, on the PBM, position-based model, so if you remember, PBM tells that the probability of the click is simply the probability of examining the rank, which is only dependent on the rank, times the relevance. So basically, the PBM considers that the probability of examination of a rank depends on the rank it only and not on the whole state, not on the whole list. There are other click models, such as, for example, the cascade model or DBN models, that are more complex and tell that the examination probability or the exposure at rank K depends also on the relevance of previous documents, because it's linked to satisfaction. Examination is linked to previous satisfaction at previous rank. And if you are satisfied by documents or items higher in the list, there are less chance to be for an item to be visible. It's very intuitive. So in the case of PBM, so as I told you, gamma K sigma could be simplified. Gamma depends only on K, so I notice as gamma of K. The exposure that ranking sigma offers to an item is deduced accordingly. So it's simply the exposure of the rank that sigma gives to document D. And in the case of the PBM model, it's only that it's the exposure parameter, which is a constant for each, depend only on the rank, which is so the exposure of the rank, where D is with sigma. So a ranking policy, the policy in this case is a distribution over ranking. So a distribution, or if you prefer, a convex combination over ranking. And so consequently, the expected exposure of an item under a policy that depends only on the context and is simply the weighted average of the exposure given by each of the ranking that are drawn from the distribution P of X. That's simply weighted average for each ranking in the support of the policy P of pi of x. So this is important because we know that we will not play with one single ranking, but a policy, so a distribution over one. The utility measures, it's just a generalization of the NDTG, for example. Very often in IR or recommendation utility of a ranking, given a context, is a linear function of individual rank-based measures. So, for example, which depend on the relevance of the document that is that rank. So, typically, as the form of sum over all rank of typically a discount factor lambda of k. For example, I give in the second line, the third line, the discount factor receives the DG, the discount factor of the DCG measure times the relevance of the document that is at rank k. Okay, this is in vectorial or matrix format. This is simply lambda transpose times the relevance of the relevant vector ordered by the ranking sigma. So this is simply NDCG in vector form. So I distinguish two particular cases, the DCG standard utility, but you could also decide to take for lambda, the discount factor, directly gamma k, which is simply the exposure, for example, in the PBM, which is the exposure parameter associated to rank k. This is so the probability that a user will look at that rank k. PBM, this depends only on the rank. And in that case, it's very easy to see that with a PBM model, the utility is simply the expected CTR. So prediction of the CTR, I suppose that you know, is the number of clicks. Is the number of the expected number of clicks on that ranking. Of course, now we are not playing with a single ranking, but a policy, so convex combination or distribution of a ranking. And so we should extend the utility, but this is simply the weighted average of the utility of the rankings that constitute the policy pi. And for now, we will suppose in the following, most of the time, that lambda k and gamma k are equal, just for conveniency, but actually it's not really necessary. It's just to make one choice and not double things in the presentation. And in that case, you see that the utility of a pi of a policy in the context X would also be expressed as a dot product between this vector, which is the exposure for each document. This is this is a vector indexed by document. I mean, first component of this vector is correspond to document 1, second correspond to document 2, etc. Document 5, etc. And row is the vector made of all relevance for doc ID 1, doc ID 2, doc ID 3, and so on. And epsilon pi of x is the expected or weighted average exposure that pi of x pi gives to document DI. So for example, the first component of this vector is the expected exposure that pi guy gives to doc ID 1. Okay, which is so this simply generalizes the utility from ranking to a policy of ranking. And of course, we can define the global utility of a policy, especially for learning to rank, as being the expected value over all possible contexts of the utility given this. Okay, so these are standard utility measures that generalize a bit the NDCG or other standard. So let's now focus on the first method, which is maybe one of the oldest one, which is FA*IR, FAIR, which is a bit an outsider. I mean, it was one of the first trials in the IR community to be fair ranking. For me, it's a bit a naive position or naive approach, but it works and has some intuition. So at that time, suppose that for a job-seeking platforms, you see that typically, so the companies are the user and the workers are the item. You see that, for example, I have this ranking of, I'm looking for an economist, I have a female, then only men. For an analyst, I have female, man, female, and so on, copywriter, this. So you see in the top 10, the proportion of male, female, and male candidates, and maybe for higher rankings, higher ranks. But actually, for several reasons, for regulatory reasons, or for respecting natural proportion of the population, you could impose that, no, this is not fair because, for example, I want suppose a 50-50, first 50%, 50 always at each rank. It's not necessary, it could be another value of ideal proportions. So now define a target proportion of the protected group. I suppose, for example, female is the protected group. It could be assigned to a uniform, so 50-50. It could be the natural proportion in the population. It could be given by, for example, anti-discrimination laws, as in US. And the fairness condition or fairness definition is that at each rank K, or prefix 1 to K, you make the statistical test. So, for example, at position 4, for example, but you should do this for every position. You look at the prefix of the rank from 1 to 4, for example, and you look at the proportion of male and female. And then you make a statistical test for the following H0 hypothesis that the protected group has at least the required proportion P. So, for example, suppose that the required proportion is 50%. So is it likely that, for example, it corresponds here to the fact that you launch a coin, a perfect coin, and to have odd and even faces in the same proportion? Is it likely that launching a coin, I will have, let's call the two faces, female and male, that have this proportion of female and male? And of course, it's unlikely, but still it's likely. For example, for rank 2, yes. For rank 3, it's a bit less likely, but still likely. And you understand that, for example, at rank 8, having this proportion by a binomial with parameters which require proportion 50 and 8 trials is very unlikely. So it's simply standard statistical test with that hypothesis that use the CDF of the binomial, because binomial is exactly this kind of launching process. And you test whether it's likely that a perfect distribution will generate this sequence. Is it likely that a perfect distribution, so the ideal distribution of male and female, will generate that? And so you reject the hypothesis if the p-value of this statistical test is less than the confidence threshold. So it's very easy to deploy in the sense that, to implement in the sense that you achieve this fairness objective. So try to have a ranking that at each rank, so at each prefix rank, would achieve, so fulfill this test. So we use an incremental greedy algorithm, which is based on two priority queues. Basically, we build two queues, for example, one for the protected group and the one for the non-protected groups, and where items are ranked in decreased relevant value. And we start with the queue with the highest relevance, okay? And simply, we consider that this top element is the top element of the new ranking list, which is the new fair ranking list. Then incrementally, we repeat this. We consider the queue with the highest relevant score. And there are two cases: either if I add this, the top element of this queue with the highest relevant score, maybe this new element will make the new ranking list unfair. In this case, I will not choose it, but I will choose the other queue and put the element, the top element of the other queue, the new list. It will improve the fairness of the new list. And each time we put an element in a queue on the new ranking list, we remove it from the queue. And we do this till achieving the required ranking list length. Okay, this is very trivial and easy to implement. And this achieves some guaranteed optimality. Of course, this targets more what I call the representation of issue, because there is no real question of relevance. You see, you consider that relevance is not my care, it's not my concern. You consider that you have some initial ranking, which is good, and it's not my concern I can re-rank it as I want, okay? So it's only to tackle the representation of issue. Now, let's go on another method, which is still provider fairness. So only focusing on provider side, still only on group, not individual, and still on post-processing, in the post-processing stage. Now, you will see that you are not targeting the misrepresentation source of inequity, but we want the other side, which was ensure equity of exposure. So this is the other goal, ensure equity of exposure across group. And we assume that relevance exposure parameters, the gamma vectors, are known. And even it's assumed to be a PDM thick model. And we assume two groups for simplicity, GI and GJ. So actually, the algorithms work for each for each query independently. So we will determine an optimal policy, so distribution over ranking for each query individually. So we do no amortization across queries, but we do amortization over search. So we can forget about X and leave X out of the equation. Now, the way we represent the ranking policy, we will see different examples of how we represent ranking policies, stochastic ranking policies. Here, the choice is to use a B-stochastic matrix. I suppose you don't know what a B-stochastic matrix. First of all, algebraically, it's a matrix such that the sum, this matrix contains elements only between 0 and 1, and the sum of the elements over each row should be 1, and the sum for each element on any column should be 1 as well. And actually, each entry PIG represents the probability that the policy pi will place item I at rank J. And this implies, of course, the B stochasticity condition, because the sum of the probability over all ranks should be 1, and so on. There is an important theorem, which is the Birkhoff-von Neumann theorem, that tells that every B stochastic matrix can be decomposed into a distribution over ranking. The number of rankings in such decomposition is of order n squared, or where n is the number of items in the list to be revamped. It means that, okay, if I solve the problem and am able to find the P bistochastic matrix, then I can use this the Birkhoff-Neumann theorem and associated decomposition method to translate this P matrix into a distribution of rankings, and then sample rankings from this distribution. Okay, then actually, if you come back and take the definition of utility, you remember that the utility was a dot product between the relevance and the exposure, all things being indexed by document, by item. Now the exposure is actually, you can decompose the exposure as being the product of the bistochastic matrix and times the vector of gamma, so the vector of exposure parameters. Oh yes. Okay. Okay, come back. So you could simply write the exposure vector as the product of the bistochastic matrix and the gamma vector, which is the vector made of the exposure parameters of the PBM model for each rank. And then it's very easy to show. Then you see that the utility is a linear function of the P matrix. Now let's focus on fairness and unfairness. Here, fairness is not considered as an objective, but as a constraint, you will see. So first of all, we should introduce two concepts, which is the group exposure and the policy. But to know, I spoke about item exposure. I should extend this to group exposure, but very simply, that's the average of the exposure of the documents, the average over all documents that constitute or items that constitute the group. So very simple. So it's simply the group item membership vector times the exposure of the document vector. Very simple to put it in matrix form. The group merit is simply the average relevance of the documents that constitute the group. Okay, you could define the merit by actually another function than the relevance, but monotonically increasing function of the relevance. That's called as a gain in NDCG, G of NDCG. And there are two kinds of fairness which are commonly used, either demographic fairness or meritocratic fairness. Demographic fairness is also known under the name of statistical parity, ensure that the exposure of the group should be the same, equality of exposure, strict equality. So we have written the exposure as a function of the bistochastic or unknown variables, the variable in P that we want to optimize. So telling that the two quantities should be equal is the same as telling that the difference is 0. So this gives you these constraints, linear in P. The meritocratic definition of fairness, also known as non-disparate treatment, tells that simply that the ratio of, so basically that the exposure should be proportional to the merit, or in other words, that the ratio exposure of the merit should be constant, should be the same. If you have higher merit, so because they were basically your average relevance is higher, you could have a higher exposure. So this proportionality rule can be translated, okay, just multiply by mjji and m of ji, and this is equivalent telling that this quantity is 0, and which is still linear and has more or less the same form as the previous one. So actually, it's very simple to solve the problem because it's a linear programming problem. Maximize the utility, which is linear in our variables P, such that the constraints are satisfied, and the constraints are either this one or that one, linear and P. And of course, with the constraint that P is B stochastic, namely all unknowns, so all variables should be between 0 and 1. The sum of all columns should be 1. The sum over all rows should be 1 as well. So this could be solved. By the way, a linear programming, so it has n² variables. You know that the best LP algorithms has a complexity, which is the number of variables times 2.5. So it means that the complexity is O of n exponent 5. So it's quite complex, and not really in my, n being the number of items to rank. So not really tractable for big ranking. Now, let's consider another, which is still provider fairness, strict group fairness, but now in processing. So all previous ones were either pre-processing or post-processing. This one is in processing. It's basically a generalization of a learning to rank method. So instead of learning simply a useful ranking, usefully ranked, we want to simultaneously be useful and fair. So provide a useful and fair ranking. So our training data are as usual in learning to rank a framework, namely a set of examples where we have a context, a set of items, so for example, query, a set of documents and their relevance label, okay? And we have feature associated, as you will to the couple of the query and each document, so each item. And more, so this is standard, but we have also group memberships. I call this G1 and G2, assuming 2 groups. And so now we adopt, or authors there, adopt another way of representing stochastic policy. They use what is called a placket-list distribution. So placket-list distribution is a way to sample or to generate rankings from an initial ranking, or to be more concrete, from what we call score parameters. So typically, score parameters are typically the output, for example, of deep neural networks with inputs, the features phi dx, and so the features associated at the document context, the document query pair, and parameters theta. And the placket list distribution, if you don't know, is some kind, I like to explain this as a recursive softmax. In order to generate your ranking from this distribution, you start from the first position, so rank 1. You sample, so each document has its own score given by f of phi di x theta. So you take a softmax over all documents with these scores, softmax with these scores, and then sample the softmax and have your first document. Then you remove this document from the queue, and you resample on the remaining queue another document with the same score, etc., etc. So it's simply a recursive softmax without replacement. So this is the formal probability distribution. You see the product because this is the repetition over k ranks, and this is the softmax classical function. But you see that each time we go on less and less documents because the ones that were already chosen are removed. So actually, it's very efficient and easy to sample from a package distribution. In practice, it's not done in the process in the way I was telling you. Is done with what is called the Gumbel softmax trick. which amounts to add a random noise to the scores. These are the scores. To add noise with what is called a Gumbel distribution, and to sort, simply to sort the perturbed scores. Also, computing the log probability is easy, and computing and differentiating, so computing the derivative of the log of the probability of with respect to theta can be done efficiently. This is very important for scalability. So where are we now? We should, as usual, define the utility function in the learning to rank framework, and we should define the unfairness, which is here used as a second objective. And we have a multi-objective optimization problem, trying to maximize utility and to minimize unfairness. So the utility of a policy is defined as usual, but normally here it's in the learning to rank framework, we consider for generalization purpose not a single query, but we want a policy that could be applied to any context and have a data set with multiple contexts. And so I take the average utility for each context in my data set. So that explains the sum over I over all observation in my data set. And then the utility, it's the expectation of, you see, remember, this is simply my NDCG. So this is NDCG, is the expected NDCG over all rankings that are derived, that are drawn from my policy through plaquetous sampling. Okay, so this is simply expected utility NDCG over all rankings and over all possible contexts. Okay. Then before defining unfairness, I should define exposure of a group. And for a context C, this is simply the average of the exposure of the documents that constitute the group as usual. The merit of a group is the same, is the average of the relevance of the documents that constitute the group, relevance with respect to the context X. And then, as before, where you remember, we were considering this difference, we consider that the ratio of the exposure divided by the merit should be equal to 0. It amounts to 1 to define the unfairness by this difference. You see that this difference is simply obtained, same as here. It's obtained, this is equivalent to telling that M of Jj times EP of Ji should be equal to E pi, the exposure of group J multiplied by the merit of group Ji. And so the difference should be as minimum as possible. So, so the unfairness is defined by this, actually the square of this to be always positive. And so the objective function, as I told you, scalarized multi-objective optimization, which is maximize utility minus lambda times the unfairness, lambda being or controlling the trade-off between utility and fairness and unfairness. And actually, it's a bit mathematics, but if this is as usual in learning to rank algorithms solved by gradient descent or stochastic gradient descent. And one challenge here is that the derivative in the parameters only appear in the expectation, and not in the terms themselves. And so you have to use what is called a log derivative trick that allows you to see the derivative with respect to data of this sum of expectations. You could take the expectation over the expectation of the derivative of the log probability of the placative distribution with respect to theta. This is called the log derivative trick. And so the gradient of the objective function is simply that, and could be, as I told you, computed efficiently. And typically this, you see that here even expectation over all sampling. In practice, the expectation is replaced by sampling over a placative distribution, typically of sampling size of 20. So that's why you replace this expectation by an empirical mean, so 1 over n sum over j. Okay, don't know, Nicola, normally time is nearly over, am I correct? I cannot hear you. Nicola, I cannot hear you. I think you're on mute.
Okay, how can you hear me?
So,
Che sta succedendo?
Okay. Can you hear me now?
yes, yes, yes.
More or less 5 minutes.
Okay, okay. So, okay. Now I think it's time to conclude. And one thing I didn't told you is maybe all the works we did here in NLE. I didn't want to promote our own work, but just to do a bit of advertising is really a much more elegant and efficient way to deal with that. With respect to the previous method, it's much more efficient. Remember that I told you, for example, the linear programming method was of complexity O, so complexity in n exponent 5. Here, the same method doing the same is n squared log n. So it's much more efficient. And moreover, this method can find very easily and elegantly the whole Pareto front. So the whole set of solutions that are both that are fair and useful together. So the whole Pareto front. So it's very nice, but maybe it will be in a separate seminar because I need really time to expose it. And just to what we didn't cover. Oh, sorry. Do you see my screen?
Yes.
Okay. So what we didn't cover is the consumer side fairness and the simultaneous satisfaction of consumer utility, consumer fairness, and provider fairness. There are some words, but not enough time. The fact that instead of working with true relevances, there are works, and it's relatively easy to do, that extend this framework to include to work with counterfactuality estimate relevance. I mean, deriving relevance from clicks using counterfactual estimation. I mean, basic click models that are able to transform click signals into relevant signals. And all what is called dynamic online fairness, where indeed we gradually, it's some kind of online algorithm where we accumulate relevance information by click. And so initially we don't know exactly which exposure we should go to item, because in a meritocratic approach, exposure should be proportional to relevance. But if we don't know relevance, what do we do? And so this kind of dynamic online fairness is exactly designed methods are exactly designed for this kind, where relevance is gradually refined and estimated, and exposure multi-exposure are adapted and corrected gradually to compensate for unfair or biased or inaccurate relevance estimation previously. Okay, and I'm sure there are a lot of other aspects I didn't cover. Okay, this concludes the lecture. Don't know whether we have time for questions, or in any way, you can always ping me on Zoom or simply send me an email. Maybe Nicola, you can maybe give my emails to the audience if you want.
Thank you very much, Jean-Michel. So guys, any questions? I have one. When you measure the performance of these algorithms, you have shown some utility measures. How does they relate to the user perception? I mean, what you are optimizing on in your post function and in your offline evaluation? How does it match to them, to what the end user perceives, a marginalized group or whatever?
So it's a good question in the sense that the data sets on which we can evaluate these offline are not so many. Because, as you know, especially for utility, but you understand also for fairness, because it's linked to utility, because both, especially meritocratic fairness, need the relevance, some kind of relevance. And so in practice, what we do, we use data sets where the relevance is assumed to be known and perfect and given by an external operator. So indeed, in some sense, it's not realistic, but it removes the problem of subjective user satisfaction perception. And so in practice, we suppose that the relevance is independent of the user, it's absolute in some way. And so basically that users are anonymous and have all the same needs or the same perception of relevance. And so this removes your this removes the question, the sense of your question, in the sense that we decouple this problem from the algorithm.
I see.
I know it's not really satisfactory, but if you are aware of data sets, more realistic data sets, where still offline and objective evaluation could be done, I will be very happy.
Okay, and thank you. And I have also another curiosity. What about the efficiency side of all these methods? I mean, how does it work with all these constraints and?
Yes. So for instance, the in-processing method, there is a training phase, and of course, what is expensive is the training phase, so the model training phase, but which can be typically done offline. Even if there are versions that are online, still they are then incremental. It's more incremental learning, and so not perfect learning. It's just doing one stochastic descent step each time you observe a new ranking, a new feedback. So I want to tell, so typically the post-processing, as I told you, some have very high complexity and exponent 5. So for me, it's not very realistic to launch them. But in general, it's designed, I know it's not satisfactory, but to be used as a planning phase and not online. So basically, it's typically done for head queries. Okay, it's done for head queries that you know a priori and that you plan. So it means that you can do this offline, post-processing this offline, and plan. You will sequence of rankings for the same queries inside the head query. Okay, That's the way complexity is dealt with. So in general, it's not designed to be done online, but offline.
Thank you very much, Jean-Michel. So guys, are there any questions, something that popped to your mind in between? Okay, so then Jean-Michel will send me the slides he presented today, and there will be his information, his affiliation, the email address, etc. in the front slide. So if you have any follow-up question or you want to start,
yes, okay. And very happy to do seminars on the topic if needed, Nicolas.
Yeah, thank you very much. Happy to can count on that.
Okay.
So I wish you a nice day, Jean-Michel. Thank you very much again for the lecture today, and goodbye to everybody.
Okay, thanks a lot, and goodbye to everybody, and thanks for your audience.
Bye-bye.
Bye-bye.